Welcome back, everyone, to the deep dive. We're always diving into the latest and greatest in AI. And today we're going to be tackling something that's, really changing the game when it comes to AI assistance.
Yeah, that's right. We've all seen those headlines about AI writing poems and composing music, but what's really exciting is how these AI tools are being applied to, more complex and challenging domains, like areas like in-depth research and, even helping with some serious decision making.
I think for our listeners, folks who are really plugged into these advancements and want to get that, deep understanding without all the fluffs, this could be right up their alley. We're talking about going beyond those, basic tasks and into the real nitty-gritty of how AI is going to, really impact our world.
Right, and I think that's the key distinction, right? And we're not just talking about, AI as a novelty, but as a powerful tool that can really change how we work, how we learn, how we solve problems. But, there's a catch. The current state of the art, particularly with these large language models, they still have some limitations. Like operationally, they can be quite expensive to run. And, honestly, when you throw really complex tasks at them, the success rate isn't always what we'd hope for.
Yeah, that's something I think a lot of people who are experimenting with these, cutting edge AI tools have probably experienced. There's that initial wow factor, but then you hit a wall. Either the price tag is just too high, or you need it to, do something that requires real deep thinking, and it kind of falls short.
Exactly. And there's a great benchmark for this called the GAIA benchmark. It really puts these AI systems through a rigorous set of tests. And the results, well, they definitely highlight that there's still work to be done. It's not quite the AI revolution we all dream of, not just yet.
That's where today's deep dive comes in. We're going to unpack this really fascinating new architecture called the Knowledge Graph of Thoughts, or KGoT. And this might be the breakthrough, the thing that really moves the needle in terms of addressing those issues of cost and that crucial element of reliability.
Exactly. And, I've been looking forward to this conversation. What we're going to do is really dissect KGoT. We'll get into the fundamentals, what makes it tick, what's new and innovative about it, especially for those who are into the academic side of things. And then, what does this all mean looking ahead? And, luckily for us, there's this recent study that lays it all out. We'll be using that as our guide today.
Perfect. All right, so Knowledge Graph of Thoughts, KGoT, even the name itself suggests a different approach. Now, we all know about large language models, or LLMs. Those are kind of the stars of the AI show right now. But KGoT combines those with something called dynamically constructed knowledge graphs. So what's the big idea here? Why bring these two things together?
It's all about synergy, really, bringing together the strengths of both. So you have LLMs, these incredible tools for processing language, understanding context, even generating text that's almost indistinguishable from something a human would write. But they often struggle with tasks that require a deeper understanding of relationships between concepts. That's where knowledge graphs, or KGs, come in.
Okay, knowledge graphs. Before we get into how KGoT uses them, maybe just a quick refresher. I think a lot of folks have probably interacted with them without even realizing it.
Oh, absolutely. Think about when you use a search engine. You type in a query, and it understands that you're looking for information related to specific entities and the connections between them. It knows that Earth is a planet and that it orbits the sun, which is a star. That's knowledge graphs in action.
Right. So it's like having a map of concepts, a way to see how different pieces of information fit together. So how does KGoT take this concept and really make it work for complex tasks?
The key innovation here is the dynamic construction of these knowledge graphs. So imagine you feed KGoT a complex question or, a bunch of documents. What it does is it starts building a knowledge graph on the fly. As it's processing the information, it identifies the key entities, the concepts, and then it figures out the relationships between them. It's like creating this evolving map of knowledge as it goes.
Okay, so it's not just about having a pre-existing knowledge graph. It's about building one specifically for the task at hand.
Exactly. And the real magic here is how KGoT uses LLMs not just to process the information, but to actually generate these knowledge graphs. It's like the LLM is having these intermediate thoughts, insights that help it build and refine this interconnected network of knowledge. And these thoughts, they're not just fleeting ideas, they're actually encoded into the knowledge graph as it's being constructed.
So it's like the AI is thinking out loud, but instead of just, words floating around, it's actually building this structured representation of its understanding. That's pretty neat. But for someone like me or anyone who's trying to do these AI tools, how does this actually translate into something that's more reliable, more insightful?
It all comes down to that structure. Having that organized knowledge base makes a huge difference in the AI's ability to reason effectively. Think about it. If you have a jumbled mess of information, it's hard to make sense of it, right? But if you organize it, create those connections, then you can really start to understand the bigger picture.
Right? Like having a well-organized filing system versus just a pile of papers on your desk. So it's not just about having more information, it's about having it in a way that makes sense.
Exactly. And what's really exciting is that this structured knowledge base allows even smaller, less computationally intensive LLMs to perform at a much higher level. It's like giving them a boost, allowing them to tackle tasks that would normally require those really massive and expensive models.
Okay, I'm starting to get the big picture here, but let's zoom in a bit. What's going on under the hood? What are the key components that make KGoT work?
So KGoT has this really elegant modular architecture. It's built around three main parts. First, you have the graph store model. This is where that dynamically constructed knowledge graph lives. They're using Neo4j, which is a popular graph database for this. It's great for handling those complex queries you need to navigate those relationships.
So that's the knowledge repository. But something has to manage all of this, right? What's the brain of the operation?
That would be the controller. This is where the real magic happens. It orchestrates the whole show from understanding the initial task to managing how the knowledge graph interacts with all the different tools KGoT uses. And get this, the controller itself is made up of two LLMs. It's a dual LLM setup.
Two LLMs working together. Okay, I'm intrigued. Tell me more about this dynamic duo.
So the first one is called the LLM Graph Executor. Think of it as the architect. It's the one that figures out what information is needed, formulates those queries to either pull information from the graph store or add new insights, and then processes the results to keep that knowledge graph up to date. It's also the one that ultimately puts together the final answer based on everything it's learned.
And what about the second LLM? What's its role in all of this?
That's the LLM tool executor. It's the one that gets its hands dirty. It's the one that actually goes out and interacts with all the different tools, gathering the information the graph executor needs. It might need to use a web crawler, run some calculations, or extract text from a document. It's the one that makes it all happen.
Okay, so one LLM is focused on the knowledge, and the other's out there in the trenches getting the information. It's like a well-coordinated team. So what kind of tools are we talking about here? What's in KGoT's toolbox?
Well, there's a whole suite of them, and they're all designed to address different aspects of complex tasks. There's the Python code tool. This one's essential for any task that involves calculations, data manipulation, or anything that requires a bit of coding. It lets KGoT tap into the power of Python to really crunch the numbers and get things done.
Makes sense. You can't really do complex problem solving without some number crunching. What else is in there?
There's also an LLM tool. It's like having another LLM on call, ready to provide additional reasoning power when needed. Then there's the image tool for analyzing images, a surfer agent that can browse the web and even has a dedicated Wikipedia tool for accessing structured information from Wikipedia. And for those of us who love our documents, there's an extract zip tool for handling compressed files and a text inspector tool that can extract text from all sorts of sources, including audio and video files.
Wow, that's a pretty impressive arsenal. And you mentioned earlier that this architecture is modular. What's the significance of that, both from a practical and a research standpoint?
The modularity is huge. Practically, it means that as new and better tools come along, they can be plugged into KGoT without having to redesign the whole system. It's future-proof, ready to adapt to whatever comes next. From a research perspective, it allows researchers to really focus on specific components and see how they contribute to the overall performance. It's like having a well-organized lab where you can experiment and really understand what's working and what can be improved.
So it's both flexible and well-suited for rigorous scientific study. All right, let's dive back into that dynamic knowledge graph. You talked about how it learns and evolves as it works. Can you give us a concrete example of this process in action?
Sure. Let's take an example from the paper based on a task from the GAIA benchmark. The task asks about a number mentioned in a YouTube VR video narrated by the voice actor of Gollum from Lord of the Rings, appearing after dinosaurs are shown. Now, initially, KGoT might just have a node in its knowledge graph representing Gollum from Lord of the Rings, but then the LLM might generate a thought like, hey, Gollum from Lord of the Rings is voiced by Andy Serkis.
Okay, so it's making that connection, linking those two entities.
Exactly. So it adds a new node for Andy Serkis and creates a link between them labeled with voiced by. Now it needs to find that specific video.
Right, because the task is asking about something in the video.
Exactly. So KGoT might use its surfer agent to search YouTube for videos narrated by Andy Serkis, focusing on those published around March 2018, which is when the task specified. It might find videos like The Silmarillion or We Are Stars, and then add those to the knowledge graph, connecting them to Andy Serkis with narrated by links and noting their publication dates.
Okay, so it's finding those potential candidates. But how does it actually analyze the video itself?
Well, it could then use a YouTube transcriber tool to get the transcript of each video and add those to the knowledge graph as well. And along the way, any other relevant information it finds, like the video being in VR format or maybe even comparing the different videos it found, all of that gets added to the graph, creating this really detailed picture of what it's learned so far.
So it's like a detective gathering clues and piecing them together.
Exactly. And because the knowledge graph is constantly being updated, KGoT can handle those really intricate multi-step reasoning challenges. If it needs to combine information from different sources or perform a series of calculations, the graph is right there, ready to be adapted and expanded.
It's like having a really smart whiteboard that reorganizes itself as you're working through a problem. Okay, so let's say KGoT has built up this impressive knowledge graph. How does it actually extract the final answer from all that information?
Well, there are three main methods it can use. The first one involves using graph query languages like Cypher, which is the language Neo4j uses. The LLM can actually formulate a query to ask the knowledge graph a very specific question like, what's the number mentioned in this particular video after the dinosaurs appear?
So it's like having a conversation with a knowledge graph, using a special language to get the information you need.
Exactly. But sometimes a more general approach is needed. That's where the second method comes in. Using general purpose languages like Python, the LLM can generate a Python script that can analyze the knowledge graph in more detail, maybe traverse different paths or perform more complex calculations. It's like writing a little program to explore the knowledge graph and find the answer.
And what's the third method?
That one called direct retrieval. Sometimes it's just easier to give the LLM the entire knowledge graph as text and let it figure things out. It's like giving someone a really detailed set of notes and saying, here, see what you can make of this.
So three different approaches, each with its own strengths and weaknesses. I imagine there are trade-offs between them in terms of accuracy, speed, and cost.
Oh, definitely. Each method has its own pros and cons. If you need an answer really quickly, Python might be the best option because it's very efficient. If you're watching your budget and want to minimize token usage, direct retrieval is probably not the way to go because it uses a lot of tokens. And if you're all about maximizing accuracy, well, sometimes the best approach is to try all three and see which one gives you the best results.
It's like having a toolkit with different options depending on the job you need to do. Now, the research paper really emphasizes the GAIA benchmark. What did the evaluations show? How did KGoT stack up against the competition?
The GAIA benchmark is a real test for these AI systems, and KGoT really shined. It showed significant improvements in both accuracy and cost efficiency compared to other leading methods. For instance, compared to Hugging Face agents with the GPT-4o Mini, KGoT solved almost 30% more tasks correctly. And when you look at cost, KGoT with GPT-4o Mini was over 36 times cheaper than using the full GPT-4o with Hugging Face agents. That's huge.
Those are really impressive numbers. So it's not just a theoretical improvement, it's something that really translates into tangible benefits. And you mentioned a no KG baseline. What was the purpose of that?
The no KG baseline was all about isolating the impact of the knowledge graph. They wanted to see how much of KGoT's performance was due to that structured knowledge representation, and the results were pretty clear. Using a knowledge graph led to solving almost twice as many tasks. So it's definitely a key ingredient in KGoT's success.
Okay, so the knowledge graph is clearly making a difference. But beyond just getting the right answer, what about the robustness and scalability of KGoT? How well does it handle errors, and can it scale to tackle even bigger challenges?
They put a lot of thought into those aspects as well. For robustness, they use a few clever tricks. One is majority voting. This means that when KGoT has to make a decision, it asks the LLM multiple times and goes with the most popular answer. It's like getting a second opinion, which helps to reduce errors. They also have robust error handling using things like LangChain's parsing tools to catch syntax errors and retry mechanisms to deal with temporary issues. And for the Python code execution, there's Docker containers to keep things secure.
So it's designed to be resilient and reliable. What about scalability? Can it handle those really demanding workloads?
To boost efficiency, KGoT leverages asynchronous execution, meaning that different parts of the system can work simultaneously instead of waiting for each other to finish. They also optimize the graph database queries for parallel processing, and for those really big jobs, they can even distribute the workload across multiple computers using MPI, which is a standard for high-performance computing.
So it's not just about being smart, it's about being efficient and scalable as well. Now, the paper also talks about how KGoT fits into the broader landscape of LLM research. Can you give us a quick tour of that?
Of course, they talk about how KGoT relates to other research areas like LAM integration frameworks, things like LangChain, which they actually use in KGoT, and agent collaboration frameworks where multiple AI agents work together. They also discuss prompt engineering, which is all about designing those clever prompts that guide the LLMs, and task decomposition, where complex tasks are broken down into smaller, more manageable chunks. And of course, they can't forget about retrieval augmented generation, or RAG, which is all about enhancing LLMs by giving them access to external knowledge sources.
It's fascinating to see how all these different research threads are coming together. So to wrap things up, what are the big takeaways from this deep dive into KGoT?
Well, I think the main message is that KGoT represents a significant step forward in developing AI assistants that are both powerful and affordable. It's not just about